Good afternoon, everyone. Thanks for coming here, even though it's so freezing cold here. Appreciate you guys bearing with us. And I guess I want to start by just making a simple, very interesting observation that there's a Wi-Fi here called Wi-Fi messed up, which I think is really funny and probably some interesting story there. I want to start with a quick story from the Second World War too, whereby the Allied forces keep finding that their bomber planes getting shot down, and they were trying to find a way to maximize the survival rate for those planes because these things are really, really damn expensive. So what they did was that they brought in this guy called Abraham the Ward, along with his group called the Statistical Research Group, to help them decide where to put additional armor on those planes to make them survive more likely to survive. So they analyzed the bullet holes on those planes that made it back to the base. And the original idea from different researchers was that we should put more armor, more protection, along where the plane is suffered most, had the most damage, which I think intuitively makes sense, right? That's where we got hit the most. And I see Tom shaking his head because he knows what's coming next. It's because Abraham made the observation that in fact, the planes that got shot down was not included in the analysis. So all you're seeing are the planes that made it home, and the bullet holes actually represent the area where the plane can be hit and still make it back to base safely. And it's the places on a plane where you don't see the bullet holes, that's where the planes that got shot down actually got hit. So counterintuitively, almost that's where we should be putting armor plate on the plane to reinforce them, so that more planes are likely to survive those hits and come back to the base. Just let the guys give them a chance to sit down. So this has become known as the survivor bias, and it's actually something that I've personally experienced many times in the way that many of our applications are set up in terms of monitoring and alerting, whereby we put so much focus, in fact, we only focus on the failure modes that we know about and we can easily monitor, and we think we're done by the time we have all the alerts for everything we can think of ahead of time. So how does this hook into observability, and how is observability different from monitoring? When I think about monitoring, I think about things that you're watching out for known failure modes in the system, like network I/O, CPU usage, memory usage, and so on. It's the sort of metrics that goes really well on the dashboards and so on. Whereas observability is much closer to what government agencies are doing in terms of gathering metadata about you and me and our social interactions, so that they're able to gain an insight into the system by only observing it from the outside. Hence the name observability. And in control theory, observability is a measure of how well the internal state of a system can be inferred only from its external output. And for any given system, any system at all, you're going to have a small and finite set of known successful outputs. For an API, it could be a 200 HTTP response code, or it could be a row being added to your database, or a message being sent into a message queue, and so on and so forth. And you also have a finite set of known error cases, such as a 500 response code to your caller for an API. So these things, since they're known ahead of time, they're easy to monitor, easy to measure them, to set up dashboards and so on. But then there's also things that we know is going to be bad, but we have no idea how it's going to manifest in our system, and therefore how do we then go about monitoring them. For example, if some network partition happens in DynamoDB, it's probably not going to be great for our system, but we don't really know how it's going to manifest in terms of its impact on our user behavior, on our users. And I can't really monitor and alert on these things because I don't own DynamoDB. I can't just take a look at its internal state. And worse than, there are also things that I just don't know to even look out for because I don't know what I don't know, right? And those are the bullet holes that we can't really see, but we still need to find some way to protect our method protocol planes from. And one common mistake I see people make is that when you think about monitoring and alerting for the system, they put so much emphasis and so much effort on just putting alerts on everything they can think of. Never mind the fact that this whole class of errors that you probably are not even thinking about, and you don't have an easy way to monitor either. So instead, what I think we should do instead is focus more on monitoring on and alerting on the absence of the finite and small set of successful signals that we do have. So it could be the case of we put an alert on HTTP request that does not end with a 200 or 400 error, or when there's discrepancy for a event-driven system between the message being going into the queue and the message being successfully processed. So this alert is going to tell us that something is wrong, but it's not going to tell us what actually went wrong. And that's where we need observability so that we can debug the system and figure out arbitrary questions that we didn't know to ask and plan ahead of time. In terms of actual implementation, the general consensus seems to be that you need to have a good monitoring, alerting, tracing, and logging, and so on in order to make a system debuggable and observable. And as we build more and more complex systems these days, we're also going to need more help in terms of figuring out what went wrong, because many of these user actions in these systems is going to span across many, many different services, and failures can happen in any one of those things. In terms of tooling, you have many open source offerings as well as the commercial tools, and they also try to tackle this problem for microservices. And I think to a large extent, they actually do a really good job, and they're getting better all the time. But then Amazon threw a curveball into the process in 2014 when they announced the AWS Lambda, and since then, Lambda has become kind of this Achilles heel to a lot of current set of tools and practices that we have, because almost every single one of them needs you to be able to install some monitoring daemon or agent on the box in order for them to work as intended. And with Lambda, you don't have access to the operating system itself, and therefore there's nowhere for you to actually install those monitoring daemons and agents. So a quick word about me. I'm a principal engineer at a company called The Zone, and since of July this year, I'm also one of the AWS community heroes that focuses on the serverless space. And I've also been, for the last 12 months, been putting together a video course for Manning, which I've just recorded the last chapter last week. So it should be fully published pretty soon. And I'm also an active blogger and a speaker as well. So The Zone, we are a sports streaming platform. You can think of it as Netflix, as in that you pay a monthly fee, but instead of streaming movies, you stream live sporting events. And we have over 40 different sports and more than 200 different leagues around the world. And more recently, we started to stream Serie A and B in Italy and boxing in the US. In all, we are available in 7 different countries, with Spain coming out pretty soon, and we are available on more than 30 different devices. And at peak, we see around 1 million concurrent viewers on our platform. And one of the interesting things about our platform is that it's all very spiky. As you can imagine, a match is about to start. Nobody logs in like 10 minutes before. They all log in about 10 seconds before the match starts. So we see almost nothing, and then bam, a couple of thousand concurrent requests a second. So because of that reason, we use both containers and serverless very heavily. We use containers for our critical path, where we have more control around the pre-scaling, so that we know before the match starts to auto-scale our cluster to such a point where you can handle that spike in traffic. Whereas with Lambda, it auto-scales automatically, is great, but there's also some limits, especially for Lambda specifically. You have a 500 per minute rate at which how many new containers can be spawned. And for our particular use case, we actually hit those limits pretty hard. If you want to find out a bit more about what we do and what jobs that we have open right now, we are hiring in London, Leeds, Katowice in Poland, as well as in Amsterdam as well. And go to engineering.zone.com to find out what roles we have open. And in terms of serverless, there's a number of new challenges now we have introduced to the current set of tools. I've already mentioned the fact that there's no access to the OS, and therefore nowhere for you to install monitoring agents and daemons. And those things has been running there for a long time as part of our tool chain, and they've been doing their job outside of critical path, where we're really concerned with minimizing user-facing latency. So these daemons, they will collect your metrics, collect your logs in the background, batch them up, and send them asynchronously outside of your user request handling code. But with Lambda, we've lost this ability to do background processing outside of our critical path. Another interesting thing that changed with Lambda is that before we would write our service, and our service would be handling multiple concurrent requests at the same time. So our code is managing concurrency. But as we move to Lambda, concurrency has now been lifted up into the platform and managed by the platform instead. When someone makes an HTTP request to our API, the API gateway itself is going to spawn a new instance of our Lambda function if it needs to, and the individual Lambda invocations will handle only one request at a time, which is great thing, by the way. It simplifies my code drastically. I don't have to worry about all these different concurrent executions, concurrent access to the same data in memory, and so on. But at the same time, we also lost some economy of scale in terms of how we deal with this monitoring and observability data. Whereas before, we were batching them and sending them in the batches at the instance level or the container level at least. But now, the best we can possibly hope for is to batch them at the concurrent execution level for your Lambda functions, which means in terms of the amount of concurrency that we project onto those systems that we use to monitor our systems, now there's potentially a lot higher much higher concurrency than we used to have before. Some vendors might struggle with this new level of concurrency that you are putting onto them, and others might just charge you a lot more in return. You might say, sure, that's easy problem to solve. Just use a bigger batch size for your Lambda functions, job done, right? Except it's not quite going to work. When imagine there's a spike of traffic coming in, so as in response, Lambda is going to spawn more containers to run your code, and the first invocation is always be what we call a cold start, where Lambda has to bootstrap the container, bootstrap the runtime, load your code, and so on. And if you're batching all this data about how your op function is running in between invocations, so that you only send them infrequently in bigger batch, then what happens when that traffic actually goes away? Some of these new containers are going to become idle. They're no longer being used, and over time, I think average I see about 5 to 10 minutes of idle time before Lambda will actually garbage collect these idle containers to free up resources that other people can start to use. Which means when your container is garbage collected, you're going to lose all this data you have collected but have not yet sent. So if you're batching them, and since you don't have access to the container lifecycle here, you can't react to when container is being shut down, so that you can do the final step to push up any data that I have collected but haven't sent yet. So you actually have a good chance of losing data as a result. Of course, you can just in that case send those data eagerly at the end of every single invocation. But remember, there's no more background processing. So even the simple act of sending metrics and monitoring data to these other systems have to be done as part of your function's invocation time, which means if you're building APIs with Lambda and API Gateway doesn't respond until your whole Lambda function execution has finished. It doesn't get a response back from a Lambda service, from Lambda, until your whole thing has finished, including sending all this custom data. That means your API is going to take longer to respond, and your user is going to have to wait for longer to get a response from your APIs. And you end up in this catch-22 situation whereby, on the one hand, you can suffer data loss if you are batching and sending data in the background. And on the other hand, you can add to your user-facing latency if you send them eagerly. We talk about some workarounds in this particular space, but even those workarounds come with their own trade-offs as well. Another trend that we notice in the serverless space is that more and more people are now building event-driven architectures. In fact, I was just talking in Alpha about 2 sessions ago from Randy, who was talking about how to scale your microservices using events. And I think in part this become much more of a trend with serverless, because it's now become so easy for you to build these kind of systems with services like Lambda and Kinesis. And in general, we're seeing a lot of Lambda invocations being linked together through some form of async event source, such as S3, Kinesis, DynamoDB streams, SNS, and so on and so forth. And of course, trying to trace those executions across async event sources is a lot harder compared to trying to trace invocations through a more synchronous invocation, such as an API call. So those are just some high-level challenges that the serverless paradigm has introduced to our existing set of tools and practices that we have. But it's still possible for you to make your serverless application observable. And I would argue that it's actually much easier to do it now, because a lot of basic building blocks are available out of the box from the platform. Take logging, for example. Anything I write to my for my Lambda function to send it out would be captured asynchronously by the Lambda service and shipped to CloudWatch logs asynchronously without adding any latency to my function's invocation time. So that's pretty great. So that means I don't need to manage any infrastructure pieces that I need to, and you get the log aggregation, log collection at scale out of the box. And the way they're organized in CloudWatch logs is that every function gets a matching and unique CloudWatch logs group. And inside that group, you have what is called a log stream. Every single one of these rows essentially corresponds to one instance of container running that particular function. So you can almost estimate the concurrent execution for that particular function with the number of rows with relatively similar last event time. But what CloudWatch logs is really bad for is for searching. I can't search for a particular phrase across all the logs from all my functions. I have to do that for one function at a time, which is never going to work at scale at any level of complexity. So what most people do here is that they will go to the CloudWatch logs console. They'll pick one of the log groups and say, I'm going to stream that to either Amazon's hosted Elasticsearch service, or I'm going to stream it to a Lambda function, which is what I see far more common. And from there, you can have your Lambda function ship your logs to whatever log aggregation service that you actually want to use. So that's all pretty straightforward. But one of the things to think about in this particular space is that CloudWatch logs itself is an async event source for Lambda. So when one of your functions writing to its logs and gets captured by CloudWatch logs, it's going to try to process that message with a Lambda function straight away. So meanwhile, you have all these Lambda functions running and serving business logic and delivering things for your user-facing APIs and whatnot. All of those functions are writing to its own logs, so all those logs gets collected by CloudWatch logs, and it's going to always try to trigger this log shipping function you have. So behind that, you also have all these extra concurrent executions for that particular log shipping function, which can push you probably a lot closer to your regional concurrent execution limit than you might realize. And once that limit has been reached, which by default is 1,000, it's a soft limit, so you can raise it via a support ticket. But if you're not keeping an eye on where you are in relation to that limit, it's quite likely for you to accidentally go over the limit. And when it does happen, Lambda server is going to start to throttle invocations, and you have no control which function is going to get throttled. So the risk here is that where your business critical functions that serve user-facing APIs can get throttled because you spend too much concurrency on this low priority function that's shipping logs from CloudWatch logs to somewhere else. So one of the mitigation strategy here you can have here is to set the concurrency limit for that log shipping function, and you can do that by setting the reserve concurrency setting for that particular function. I know it says reserve concurrency, but it actually means the opposite. Is the maximum number of concurrent executions that particular function can have at any moment in time. So, or a better strategy at scale is instead of having subscribing a CloudWatch log groups to a Lambda function directly, you can actually subscribe it to a Kinesis stream, which is not available through, it's not an option through the console, but is as an API call, you can do this so that every log group is subscribed to a Kinesis stream, which you then process it with a Lambda function. And from there, you can ship your logs to wherever you were doing before. And the reason why you can do this, and it's a good idea at scale, is because between Lambda and Kinesis, concurrency is controlled by the number of shards you have in the stream. So a stream with every shard in the stream would have a dedicated instance of Lambda function for a subscriber function. In this case, I can control how much concurrency I'm using to process logs by controlling the number of shards I have in the stream. Another thing to keep in mind is that every time you create a new function, you're also going to create Lambda is going to create a new log group for you as well automatically. And you don't want to introduce a manual process for someone to have to go into the console and always remember to subscribe the log group to your log shipping function. So what you can do here is enable CloudTrail, which then allows you to capture API calls that's happening in the ecosystem, even the ones that the other services are making on your behalf. So in this case, I can then use the CloudWatch events to create a pattern against the create log group API call that the Lambda service makes against CloudWatch logs whenever I create a new function, and then I can react to that event happening with a Lambda function whose job is then to subscribe the newly created log group with my log shipping function, so that this is a future-proof way to say, okay, anytime I create a new function, it will be automatically subscribed to my log shipping function, so that any logs that arrive from this function will automatically get shipped to my log aggregation service. And if you're using serverless framework, you can also just include a few lines in your serverless or YAML so that you can deploy this whole infrastructure to any new account that you create. Another thing to keep in mind is that when the new log group has been created in CloudWatch logs, the default retention policy is to never expire any logs, because AWS doesn't want to touch people's data, they don't want to lose any data, which is good. But then again, if you're shipping all of your logs to somewhere else already and you're paying for that other service for storage and processing, why do you want to pay for storage in CloudWatch logs still? And the fact that it's never expired, that means the 3 cents per gig per month you're going to be paying for is going to keep getting bigger and bigger every month. So you should apply the same pattern here and just have another the same CloudWatch pattern, but have a different Lambda function whose job is then to change this default retention policy to something more meaningful for you, maybe 7 days. And probably one of the most important and easiest thing you could do as far as logging is concerned is just write structured logs. And one of the things I keep noticing is that, I was talking to many different people, is that we tend to forget to do this when we move to serverless, partly because we don't need to use those traditional logger anymore. They're quite, I mean, personally, I find them too heavyweight an abstraction for Lambda. But at the same time, many of those practices that has come along with those loggers has also been forgotten along the way as well. Even though we have made the same mistakes in the past, we have learned those mistakes sometimes in the hard way, and we actually know how to do this pretty well nowadays, how to write good structured logs. And even in the world of serverless, structured logging is still very much an essential part of making your system observable. You want to attach as much context as you can with every log message. And like I said, I do find that many of the traditional loggers that you use for whatever your language you're working with to be too heavyweight for Lambda. Most of these things support different output locations, file console to some log service directly, or they do rolling file support and all that. And I don't really need any of that. All I need is some abstraction that allows me to write to consoles to send it out and support structured logging. So what we do internally at the Zone, we have a very small library, which is part of a bigger set of tools I will talk about pretty soon, that integrates with how we manage correlation IDs and most importantly, it supports structured logging with JSON, and this is quite crucial later on. It allows me to control the log level with the environment variables, and not the Lambda environment variables, which requires a deployment for you to change. But this is the node process environment variable, so that I can actually change the log level for specific invocations. Because one of the downsides with doing structured logging is that you're writing a lot more data now to CloudWatch logs, which, as I mentioned, has a cost associated with that. You pay 50 cents per gigabyte of data ingested, which on the face of it may not sound a lot, but consider that for a Lambda function that's 128 meg that runs for, I think, 1 second, you can actually get 1 million invocations for less than that. So relatively speaking, it's still quite expensive for how much money you're spending for ingesting logs from your functions. And if you log everything in production, it's quite common, and I've seen this quite a lot with people, with my clients as well, that you end up spending a lot more money on CloudWatch logs than you do for your Lambda invocations in production. And one of the hard lessons that many people have learned is that in production, you just don't want to be logging everything. A lot of the debug messages are just not useful. But then again, what happens when something does go wrong, and we know we can fix this problem if we have the debug logs in the first place? So you also find yourself in a situation where sometimes you have to go back, enable debug logging, deploy so that you can collect enough debug messages to actually figure out what the problem is, so that you can fix it, redeploy it, and so on. So not having those debug logs handy also means you can now increase your mean time to recovery. And inside a microservice architecture that you build with a serverless, chances are problem can exist in any number of these places, and you want to collect all the relevant debug logs for entire user actions or transactions or workflows or whatever you want to call it. And that means potentially you have to enable debug logging on many different Lambda functions in different projects across different service boundaries. And after you're done, you still have to remember to disable them and redeploy to production. So it just adds a lot of overhead in terms of what we need to do. So a much nicer compromise, a better compromise would be between having no visibility at all because we don't have any debug logs in production, to spending too much money on CloudWatch logs because we're logging everything, is to just sample a small percentage of your debug logs, say maybe 1%. That seems to be quite a common thing people want to do. And one of the things you could do is, and this is what we do internally, is that we have a middleware that allows us to make this very easy to implement. And in this case, if in the Node.js world, there's a middleware engine called MIDI, which in this case allows me to write a middleware that remember my logger allows me to change the log level on the fly by modifying the environment variable. So my middleware will change the log level to debug for, say, 1% of invocations before executing your function's handler code, and afterwards it will change it back to what the log level was previously. And this is possible, and only possible because now in Lambda, we don't have to deal with concurrent requests in the same invocation. So concurrency is in a platform, and one Lambda function just deals with one request at a time, which means it kind of acts like an actor in the actor model, and I can modify global state safely without worrying that, oh, maybe potentially I can end up enabling debug logging on some other concurrent executing request happening somewhere else. And inside my middleware is just that simple. All I have is a before hook, where before the runs my function code, I decide check whether or not I should enable debug logging. In this case, based on the probability, and then once I enabled it, when after the invocations, after your code has finished running, then roll back the decision to what the log level was previously. And when an error happens, when a function errors for some reason, I also want to capture the invocation event itself, in this case as a JSON payload along with the request ID, so that I can capture those failed invocation events and replay them offline, potentially by running my function locally against that invocation event that I have managed to capture. But then again, this sampling decision needs to be propagated all the way across the entire call chain. Otherwise, you're going to end up with any number of transactions or workflows. You're going to have the debug logs here, but not here. So you still can't figure out what actually went wrong. Or you may have the debug logs here, but not in this guy or this guy. So wherever the first function in the whole call chain needs to make the decision to, okay, do we sample debug logs for this entire call chain, and then propagate that decision to all the other places, all the other functions in the same call chain. And then you want to make sure that those you want to also pass other correlation IDs along, so that it gets propagated throughout, and it gets included in all the logs for all from all the functions. Correlation IDs including the initial request ID going into the first function, as well as things like user ID, session ID, order ID, or whatever that makes sense for your particular workflow. And I also like to capture the user agent as well, because when I'm processing some event in some kinesis function, really further down the call chain, and if something goes wrong, I want to be able to see quickly what device or what platform the request originated from. You'd be surprised the amount of times I see, okay, this payload doesn't make any sense. Look at the user agent. Turns out someone sent a request from Postman. They're trying to test against production with some arbitrary payload. And for this to really work, we need every function to do the right thing and be a good citizen in our ecosystem and propagate information along with such as correlation IDs along to other APIs and other streams and other queues and other SNS topics that it talks to. And that means that I need to, when I have so many different teams all building their own functions, all running and operating their own functions independently, I need to have tools that make it easy for teams to do the right thing as default. And in terms of these tools, I want it to be non-intrusive to my developers, and I also want to allow my developers to introduce new different correlation IDs into the mix, and it should work consistently across different event sources for Lambda, including streams, which requires some special handling because events are processed in batches. So when you receive a batch of records from Kinesis, every single record is going to have a different set of correlation IDs because they're all part of a different transaction or user or workflow, and you need to be able to swap in and out different correlation IDs as you process different records. And remember, concurrency is not in our code anymore, so we can leverage that fact, and that we don't have to deal with concurrent requests in the lambdas by storing those correlation IDs in a global state. In this case, we have now a static and known location for our logger and other tools to find out what are all the correlation IDs that's been collected for this invocation so far. And we just have a very simple library that provides a thin layer of abstraction over what global variables that we are using, that allows you to get and set correlation IDs by key, and also allows you to swap in the entire set of correlation IDs, which is useful when we try to bootstrap an invocation by inspecting the invocation event and extracting correlation IDs from that. Which is what we're doing using a middleware that makes it easy for us to makes it easy for correlation IDs to just flow through your function without you have to consciously think about, okay, every single time when I write a function, I have to remember to extract the correlation IDs out somehow. So in this case, our middleware will run before my function handler code runs, and it's going to inspect the invocation event. And based on the event source, if it's an API gateway invocation event, then I know to look for the correlation IDs in the headers. And if it's SNS message, then I know to extract the correlation ID from the message attributes, and it knows how to handle different event sources. And right now we support API gateway, SNS, Kinesis as event sources, but also direct Lambda invocations as well as invocation against step functions. And as a developer, that means I don't have to constantly remember to include those correlation IDs in my logger, because my logger is always knows where to grab those correlation IDs, so that anything I log will include those correlation IDs as part of the message. And we also have HTTP client as well as a wrapper for AWS SDK client that would automatically forward those correlation IDs on when you talk to other services from your function. So as a very simple example, as a request coming in from a user through API gateway to my Lambda function, I will capture the request ID and use it as my correlation ID, so that when my function uses the HTTP client to talk to another endpoint, the client would automatically include the correlation ID that's been captured in the header as it goes out to the endpoint, so that the function on the other side will know to find the correlation IDs in the headers and includes it in all of its own logs as well. And all of this hinges on the fact that there's a known location for storing our correlation IDs during an invocation, and we actually built a whole set of tools around this so that as a developer, all I need to do is apply one single wrapper of my function, and I get sample logging, and I get for the entire call chain, and I also get the correlation IDs being auto captured and forwarded on, and you have a logger that automatically includes all of my correlation IDs in every single log message that I write for my function as well. And so all of this comes with minimal effort from me as a developer, and the idea is that the tools would just do the right thing by default. How are we doing on time? Okay, I think we're doing okay on time. And in terms of monitoring, you get basic telemetry about your functions from your CloudWatch metrics, including function invocation count, duration, error count, and so on. And oftentimes, you also want to send custom application level metrics as well. But remember, there's no more background processing, so you can't do this outside of the critical path. So you now have to send metrics to CloudWatch if you're using CloudWatch during your function invocation, which means that you have slower API response time. But you might say, hey, that's what, 10, 20 milliseconds API call to CloudWatch metrics, not a big deal. The problem comes when you've got microservices whereby those 20 milliseconds per API call can start to compound. And one user action might involve many API calls to different services. We might call your backend for front ends API that you've set up, but then that might call multiple APIs along the way. So if every single one of those API calls has an extra 10, 20 milliseconds, it's quite easy for you to end up with more than, say, 100 milliseconds added to your user-facing latency. And Amazon actually found that every 100 milliseconds you add to your user-facing latency can impact you in terms of the number of cells by as much as 1%. So one of the workarounds you can do here, and this is what Datadog does out of the box, is you can actually record those custom metrics as specially formatted log messages. And remember, since CloudWatch logs capture all these logs asynchronously without adding overhead to your function's invocation time, you can piggyback off that process and have your log shipping function just filter those guys out and send them as metrics to your monitoring metric system instead. Or if you're using CloudWatch logs, you can also have, if you're using CloudWatch metrics, you can also set up a CloudWatch filter metric in your log group as well. This sounds a bit wacky to use CloudWatch logs essentially as a way to do background processing, but this is what we have had to do given the current limitations in the platform. Things are likely to change in the future, but right now this is what a lot of tools that are designed with serverless in mind are already doing. So the trade-off here is that you're adding additional delay to seeing your metrics in the dashboard because you have to go through another hop in the process, and you're also adding additional cost to the use of CloudWatch logs in terms of the amount of data you're ingesting, and you also have to worry about managing the concurrency for that log shipping function. But in return, you are removing all the latency overhead you're adding to your function invocation time to collect custom metrics. It's not the right trade-off for every single situation, but I think when you're building APIs where the latency is user-facing, you should definitely consider this approach if you're concerned with minimizing user-facing latency. But if you're doing background processing with Kinesis and Lambda or SNS and Lambda, then the additional latency is not user-facing, so just don't bother with that. Just go straight to the monitoring system and record those custom metrics. And once you have everything in one place, don't forget to set up dashboards and set up alarms and hook them up with PagerDuty or Opsgenie or whatnot. And if you're using Datadog, then many other providers also do the same thing as well. They support ingestion of metrics from CloudWatch directly. In the case of Datadog, they also can pass those special log messages and turn them into metrics instead. And that brings us to tracing. In terms of tracing, Amazon has got the X-ray service out of the box, which supports the Lambda and API Gateway and a few other services. And in this case, I can instrument my code so that I can trace through what happens inside a function to see where those invocation time are being spent, especially if I take the time to actually instrument my code really clearly so that I can see the various different steps, how much time it took to talk to SNS, S3, DynamoDB, and how much time it took talking to another API another Lambda function behind API Gateway, which was something that they added a little while back. And you also, with X-ray, you get this service map view, which just gives you a very high-level view of the different things your function is talking to, and also what sort of average latency you're seeing from those things. One of the shortcomings with limitations with X-ray is that it doesn't span over async event sources. And as we talked about already, so many people are now building event-driven architecture using Kinesis and Lambda, and you lose visibility from X-ray's perspective as soon as your function goes into one of those async event sources. You do get different traces but they're broken down as opposed to one big trace. You're going to see the bit that's from your APIs talking to Kinesis, and then the Lambda function after that is going to be a separate trace, which doesn't really help when you try to understand what happens for an entire user flow, for an entire workflow. Another limitation with X-ray being an AWS service is that it doesn't support non-AWS services. I know for a fact that many people use with Lambda services that are not AWS. Things like Auth0 is very popular as authentication service, which I find a lot easier to work with than Cognito. And this is where I really like the stuff. This is such a problem that many providers are working on, and I particularly like the stuff that the Epsilon guys have been working on, have done with their product, which is much more focused around not individual functions, what happens inside individual functions, but what happens on the entire workflow, those entire user transaction. And it supports async event sources as well as non-AWS services, such as, in this case, you can also see GCP's natural language service, as well as your functions and Auth0 and so on. And they also support workflows in the step functions as well. And I think that's all the time I have for this. And if I want to leave you with a couple of simple things you should take away from this, I think probably the most important thing you could do, and the easy thing you could do, is just make sure that you continue to write good structured logs from your Lambda functions, and also take the time to instrument your code so that you can get as much context as possible, and so that when you're using tracing services, you can get as much breakdown in what happens inside your function as you can. And at the minimum, you should instrument all the code around integration points you have where you're talking to other services. And if you want everyone to do the right thing in your company, then make sure you invest into good tooling to make it easy for people to do the right thing as default. A lot of things, as I mentioned, a lot of things I've been learning. I've learned about running AWS Lambda in production. I've been putting them together in the video course for Manning, including all the things we talked about, but also things like CI/CD, VPC security, and how to do canary deployments and so on. And I'm also running a workshop as build stuff on Sunday. Come on to that if you want a more sort of in-person classroom session. With that, I think just out of time. So thank you guys very much for your time and for bearing with the weather conditions here.